So we're going to finish off our work from yesterday, which was our last lesson, which was finding second derivatives. So in this question we have e to the sine x is y. If we take our first derivative, remember the derivative comes out the front, so cos x, e to the sine x. And if we take the second derivative, you'll notice that we have to use the product rule here because it's actually two functions together. So we're going to basically let one equal u and the other one equal v. So cos x is u, v is e to the sine x, u dash is negative sine x, and v dash is going to be cos x, e to the sine x. Oops, like that. I'll just move this over a little bit. There we go. So now when we look at this question, we've got our v, u dash, and v dash. So we basically just use our rule, u dash v plus v dash u, and substitute everything in. Now you'll find that when you do this, there's not really that much in common except for the exponential part. When you multiply these two together, you get a squared cos because there's two of them. So really about the only thing you can do here is pretty much just take e to the sine x out as a common factor and then just have the trig like that. Now the other question we've got here is inverse tan. This is really ugly, this one. So basically because we have y equals inverse tan of something, we're going to let that something be u. So I'm going to write u as 1 on x minus 1, or it's going to be easier to write it like that. So now when we do dy du, you know that the derivative of inverse tan is 1 plus 1x squared. In this case, it's going to be 1 on 1 plus u squared. And du dx is going to be negative 1 x minus 1 to the negative 2. So now that you've got that, we're going to find dy dx. Now dy dx is dy du by du dx, which is, now this is the bit that's fairly ugly. It's going to be this thing. Now u is actually this thing, 1 on x minus 1 all squared times negative 1 on x minus 1 all squared, like that. Okay, so it looks quite ugly at the moment, but we're going to simplify it a little bit. So on the bottom over here particularly, let's make all of this have the same denominator. So you'll recognize here that this has a denominator. I'll actually show you the expansion so you can see, but it's going to be x minus 1 all squared, because this becomes, when you expand the squaring on the bracket, becomes that. And the second thing we haven't done anything to yet. So now I'm going to make everything have a common denominator here. X minus 1 squared would be the common denominator that you'd want to have. So put it all over x minus 1 squared. Now the thing that happens here is you've got basically 1, it's essentially like a fraction on a fraction. So the reason for that is 1 is like 1 on 1, and then you've got this like 2-layer thing going on here. So this is actually going to flip over. So you're going to end up with x minus 1 squared on the top, x minus 1 squared plus 1 on the bottom, because this goes up, and then it looks like that. These guys cancel, so you now have this. And if you expand that out, it looks like this, which looks like this. Now, that's a really awful thing for y dash to be, because it now seems like it's going to be awful to differentiate. But I'm actually going to write it out in a slightly different form, which is to write it out like that. Bring it up. So bring it up to the top line. It actually means y double dash is much easier to do, because now it's like the power comes out the front, so it's a negative times a negative, which we know is a positive. We multiply by the derivative of the bracket. Derivative of the bracket is 2x minus 2. The bracket itself stays the same, and then the power goes down by 1. So after all this work to get the first derivative, the second derivative is actually much easier. So we're going to go on to 6e. So this is looking at what the second derivative tells us about a graph. So basically, if you look at your second derivative, if your second derivative is negative, so that's what this is saying, if your second derivative is negative, it's going to be what we call concave down, or like a frowny face basically on the graph. If your second derivative is positive, then it's positive like a smiley face, and you're going to have this concave up shape. The other cool thing about concavity is that if you have a point of inflection is where the concavity changes. So for example, negative to positive, and you have a point in the middle. Where that happens, you're going to have a point of inflection. So to find a point of inflection, what you need to look for is actually if the concavity changes. So what we do is we do our second derivative, and we actually check where the second derivative is 0, because if your second derivative equals 0, it's possibly going to be a point of inflection, but you're not sure. What you have to do is you have to check that the sign of the second derivative goes from negative to positive, like that, on either side, or alternatively the other way, like positive to negative. So if it's backwards. So you actually have to check the sign change. The other really useful thing about a second derivative is that if you have a stationary point, like something like that, if you want to check whether or not that stationary point is a maximum or a minimum, you can actually chuck it in to the second derivative. So let's say at x equals a you have a stationary point. If you actually chuck that point a into the second derivative and it is negative, then you actually have this concave down, so you know that the point is a maximum. So you don't have to do that checking each side of the gradient thing that you have to do with the first derivative test. And you can do it similarly if you had a stationary point, if you had something like that. Say this was at x equals b, this stationary point. If you put that value into the second derivative, you'll find that you end up with a positive value, and that tells you that you have this concave up. It tells you that you have a stationary point that's a local minimum. So that's the 2 points here that are on your notes, which you'll want to highlight, and you want to highlight that point as well, making sure that you check the second derivative is 0 for a point of inflection and check that the signs change. So we're actually going to work on this question here, just to get an idea of it really quickly. So basically we have a graph that's been given to us, so it's kind of already given it away, but we're going to do a couple of things just to check it out. We're going to do the derivatives, first and second derivatives, and I'm going to give you a few pointers here on what you should do. First thing you should do with something like this is once you've done your derivatives, I'd factorize. Don't factorize before, because otherwise it's really awkward to do the derivatives, but once you've done your differentiation, I'd factor it. So you can see here the 3 and then a minus x there, and the 12x, which is 2 minus x there. So now we're going to look for a few things. The first thing is we're going to look for any stationary points. And we do this by looking for any points where the first derivative is 0. So we know if this is the first derivative here, it's really easy to tell when the first derivative is 0, because you have to find x values that make this 0 or that 0. So straight up, at x equals 0, you're going to have your first derivative here being 0, because that becomes 0, and at x equals 3, because that's going to make that 0. So if you then put those values into your function, your original function, you'll get 0, and at 3 you'll actually get 27. So that means you have stationary points at 2 places, at 0, 0, and at 3, 27. Now what you can do to actually check the type of stationary points they are is you could do this second derivative test, So if I put the stationary point, do the first one, 0, into the second derivative, do you see that it actually ends up being 0? It's not negative or positive, so we don't actually know what type of minimum or maximum that is. So we don't get any information out of that. But if I put 3 into the second derivative, which is here, I'm going to get 12 times 3 and 2 minus 3. So 12 3s are 36 times negative 1, it's negative 36. So because this is negative, and negative means this kind of shape, so that means that I know this stationary point is going to be a maximum. So it's this frowny face, negative here. So it's really handy because even without the graph, you can tell from the graph because it's there, but you'd be able to tell the type of stationary point. So that explains this part of the graph here. And obviously you could find your intercepts here too. When y is 0, it happens at 4 and 0, so at these 2 points. You know that this is a quartic. It's also a negative quartic, so it's going to be that sort of M shape. So far we've deduced that part. We don't know what's going on here yet. We're going to look for any points of inflection. So when we do that, the second derivative needs to be equal to 0. And if we set that, you can see from the second derivative that that happens at x equals 0. And it also happens at x equals 2. Now we know that the point 0, 0 from here was already a stationary point. This other point, which is when x equals 2, and if you actually put that into y, you'll get 16. So I'll put that there. Put 2 into y, you'll get 16. So we have 2, 16. We actually need to check whether these are actually points of inflection or not. So to do that, we need to check that the sign changes either side. So I'm just going to delete this part over here so we can do that. So the best way to do this is with a table, and I find that because you've got 0 there already, and you've got 2, you want to check either side of those. So what I would do is I'd check, this is going to be the x values here, and we're going to check the sign of the second derivative. I'd check at -1, 1, and 3. Now we know that the second derivative is equal to 0 already at these points because they're possible POIs, but we're not sure. And in terms of concavity, the shape, we basically don't know what's going on at these points here. But we're going to be able to look at concavity at these other points. So the first one, we know our second derivative, I'm just going to write it here so you can see it, is 12x 2 minus x. So when we look at the second derivative, for example, at -1, it's chucking -1 in here, you're going to have -12 and -2 minus -1, which is 3. So it's going to be a negative value. It's -36. Now negative means the concave goes like that, concave down. So we're going to do a check on the other side of 0. So imagine if you chuck in 1 into there, you're going to get 12 times 2 minus 1, which is 1. So that's 12. That's a positive number. It's concave up. You can see here that this particular point at 0 has this shape around it. It goes like that because you've got concave down and then concave up. So this is actually going to be a point of inflection, that one. This is a point of inflection. We're going to check on this side though as well. Let's get rid of that. So we'll check what happens at 3. So we've got second derivative at 3, and if we do that, you're going to have 12 times 3 and then 2 minus 3, so that's going to be negative. So yeah, that's a negative value. It'd be -36. So because it's negative, you've got this. Now you can see that this other point here has a concavity that's like positive, then it's flat, then it's negative. So this is actually a point of inflection as well. So both of those points are points of inflection, and that's why on the graph you can see there's a change of concavity here, like that. There's also a change of concavity here. But what you'll notice is that this other one, the one at 0, 0, is much like more obvious. The reason for that is simple. This point here at 0, 0 is actually two things. It is a point of inflection and it's also a stationary point. So because of that, it's what's called a stationary point of inflection. It's two things. It's actually where you have both a leveling off of the graph and a change in concavity. A normal point of inflection doesn't have that. It's just a change in concavity. There's no 0 gradient there. At this point here, the gradient is 0, but not in this one. And a local maximum, we know that that's, again, where you've got the first derivative is 0. So point of inflection, you don't have that happening. That's why that point of inflection there at x equals 2 didn't pop up here. So that's the idea with being able to tell a lot about a graph. So we're going to do a few of these really quickly. So we've got our first function, 2x cubed plus 6x squared minus 12. Find the first derivative, so y dash. And second derivative, I'm going to factorize again. So factorize like after you've done all the differentiating. It's much easier for you to be able to tell what's going on. There's actually not much I can do with that. Okay, it says use the second derivative to find the coordinate of the point on the graph where the gradient is a minimum. Now the gradient being a minimum is the point of inflection, because that's where, if we go back to here, that's where you've got like gradient, steep, 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 change in concavity, and then going back again. So that's where our gradient's a minimum. So to find your point of inflection, you need to let your, for POI, you need to let your second derivative equal 0. That happens when the second derivative equals 0. That happens at x equals -1. Now remember, we need to check whether or not that's actually a point of inflection. So check a couple of values either side, like -2 and 0 are good ones. So in your second derivative, which is here 12x plus 1, put in like -2. So if you put -2 in here, you're going to get -2 plus 1. It's going to be negative. At 0 there. So negative concavity, no concavity. And then at 0, when you put 0 into this second derivative, you'll get a positive. So that's cool. So this is a point of inflection. So now, because it's asking you for the coordinates, you'll need to substitute that -1 into your original function. So just chucking it into here. And remembering that when you have a negative to a power, if the power is positive, it's going to become positive, and if it's negative, it'll be negative. So this will be -2 plus 6 minus 12, which is going to be 4 minus 12, which is -8. So our coordinates would be -1, -8 for that point of inflection, or minimum gradient. It says here, sketch a small portion of a continuous curve around a point x equals a. I'm just going to chuck, here's x equals a. It says here the derivative is less than 0. Now if the derivative is less than 0, it's not a turning point, because that would be equals 0, which it's not. So we know that the gradient being, not less than 0, bigger than 0, means that you have a positive gradient. So it's going up, the shape's going up. It also says the second derivative is greater than 0. That means you have positive second derivative, which means positive concavity. So the actual shape of the graph at this point, x equals a, would be not only a straight line because of the positive gradient, but it would be curved straight line because of the concavity here. All right, the next one, you've got a parabola. Show that the parabola with the following equation has no points of inflection. Well, we're going to differentiate that 2 times and see what we have, because we know the second derivative is what we need. Now remember that we need to set the second derivative equal to 0 to find any points of inflection. But if we set the second derivative equal to 0, there's no x values here, because it's only the 2a, the constant parts that are left. So because of that, there are going to be no values of x where this thing is 0. And that means that your second derivative, presuming that this is not going to just disappear, your second derivative is never going to be 0. So there's no x value you can put in here to make it 0, because there's no x's there. So that's why there are no points of inflection. This one here, I actually, just because we've done quite a bit of it on the other pages, I wouldn't worry about that one. We'll just go on to the next one. So for this one, we've got determine the coordinates of any points of inflection and the gradient of the graph at these points. Again, it's really easy. So the gradient of the graph is just your derivatives. I'm sort of doing them at the same time just because they're kind of asking the same thing. And then it's asking for points of inflection. So remember that the key thing for points of inflection, I know this is something that's looked at in exams, is that you need to show that the point of inflection actually changes signs. It's not enough for you to say, okay, look, I found where it happens. Like, for example, here you let the second derivative equal 0 on each, and you say, okay, well, that tells me that here 12x squared equals 6, x squared equals 6 on 12, which is a half, x equals plus or minus 1 on root 2, which is plus or minus root 2 on 2. So we've got the points of inflection, possible points of inflection, so we always have to do the check. That's important. So we have to check the concavity either side, okay? So you have to check the sign of the second derivative. So what we do is we'd actually go, okay, we've got x, we check it at 0, we check the sign of the second derivative, and then we check the concavity. So I'm just going to do this in a different colour. So I know that at 0, we know that the second derivative is 0, so there's no concavity. When we have, say for example, -1, we're using this second derivative here. So when we put -1 in there, you get -6, so it's negative concave. If you put 1 in there, you get +6, positive concave. So this is a point of inflection because it changes concavity. And we know that when we put 0 into the original, we get 0. So we have 0, 0 is a point of inflection. Now this one's a little bit more ugly, and oh, I've noticed here that I messed up, which is why it's probably good not to do 2 at once. So what have we got? 12. That's much better. So the nice thing about that, it sort of troubled me because I was thinking it just seems like a really ugly answer. So we've got that. It's like that. Let that equal 0. That happens at x equals plus or minus 1. So because we've got 2 points here where we're looking for possible points of inflection, what I would do is I'd set this up as a table where you check them all at once. So the 2 that you're possibly checking are -1 and +1. So you can check points in between, like conveniently, by doing that. And check the second derivative. Now we know that this is our second derivative here. 12x squared minus 12. And so if we put in -2 into here, we're going to get -2 squared is 4. 4 minus 1 is 3, so this will be 36. That's positive. It's going to be concave up. At -1, we actually have a 0 second derivative, no concavity. At 0, if you put 0 in here, you're going to get 12 times -1. It's going to be negative concavity. And at 1, the second derivative is 0, so no concavity. If we put 2 in here, 2 squared is 4, minus 1 is 3, and that's going to be positive. So you can see you've got up, and then you've got down, down, up. So actually both of those are points of inflection because their concavity changes either side. You have this kind of shape or this kind of shape. So they're both points of inflection. So that means then it would be a matter of putting both of those into y to get your, y coordinate. So like that and like this. -1 to the power of 4 is going to be 1, and it's also going to be the same here because it's squared. So you're actually going to find that both of these answers, which is -6 plus 4 is -2, so it's -1. You're going to find your coords for both are actually 1, -1. They have the same y value. And -1, -1 are your POIs for that particular example. Oops. So the last one that we've got here is again finding a couple of things. So finding the derivatives. So we're going to find first of all the first derivative. Now this actually has 3 parts to it. So what I'm going to do is I'm actually going to, we could do a couple of things here. The first thing you could do would be to expand the x through here. Instead of having 3 terms, you'd then have 2. Okay, then you could use product rule. You'd have to use product rule a couple of times, but I'm actually going to use the Mathematica here. So I'm going to use the CAS. We're actually going to use the CAS for this whole question, I think, just because it's going to be a bit long otherwise. So we'll do that.